everybody. Thank you so much for joining us for today's webinar. We are so excited to get started. We still have a few minutes until the webinar starts, so y'all can get settled in. I'm just making sure that everyone can chat right now. So, as people kind of filter into the Zoom room and get comfortable, I'd love to kind of tell you how we're going to run this webinar. So, to ask your questions, and we do want to hear your questions, please feel free to navigate to the bottom of the Zoom window. You'll see a little button that looks like a chat bubble from a comic book. Go ahead and click that, and that'll open the chat. That's where you can ask us your questions. So make sure you're dropping your questions in the chat. My other big request is that you click that blue button next to the to section and just make sure it's set to everyone instead of hosts and panelists. As we answer your questions, we want to make sure it doesn't look like we're talking to ourselves. So please make sure your set or your to is set to everyone. That way we can also knowledge share. Some people might be wondering the same thing. So they can say, oh, thank goodness, someone else was wondering this, or you might inspire another vein of thinking. So make sure you're kind of opening that conversation up to everyone in the webinar today. And in an effort to practice this, go ahead and open that chat window, select everyone next to two, and let me know how is the end of the school year going for you all? We were just chatting about how physics AP exams are going right now. So, yep. Barbara says that they're busy. Yep, that totally makes sense. Oh, Rebecca says, oof, and that is really fair. Full of so much state testing. Yep, David, that's right there with you. Julia from Indiana says that they are busy. Yep. Fire emoji. Yeah. If only they had an emoji for like a burning dumpster. I remember when that was a big thing. Summer school starts next Tuesday. No time to think about what ended. Laura, I totally hear that. It is just, yeah, one thing to the next. Man, how's everyone else doing? Oh, laughing emoji. Yep. Going great. Love to hear that, Russ. Yes, carrying it strong through the end of the school year. Man, well, we are about a minute past the hour. I'm sure we'll get a few more people. For anyone joining us late, we're just chatting in the chat window here. That is where you can ask your questions. And as we get started, I'll go over some housekeeping items with you all really quickly. So if we can pop to the next slide, perfect. Anyone who registers for this webinar will get a recording. It usually takes us about 3 to 5 business days to get that edited and uploaded to YouTube, but as soon as it's ready, I'm going to email out a link to you. In that email, you will also get a link to a resources folder. I'm going to drop that link in the chat as soon as I'm done talking. In that resources folder, you'll find free experiments, you'll find today's presentation so you can follow along. I have a certificate of attendance in there, so make sure you use those resources. Like I said, I'll get the link to you in just a moment. Please ask your questions. We have amazing presenters here who are ready to help. Drop your questions in the chat there. If we happen to not get to a question of yours or you think of something after the presentation, please reach out to us. You can reach us at physics@vernier.com. With all that being said, oh, I forgot something, but I knew I was going to. I'm going to ask you to fill out a survey at the end, so keep an eye out for that. We also are doing a giveaway, so stay till the end and you might win something. And with all that being said, I will now hand you off to today's presenters. Thank you again for joining us.
Well, hello, everybody. I'm Fran. We were supposed to have Tom Smith here with us today, but he was not able to make it after all, but that's okay. We got everything ready. So I am the director of physics here at Vernier, and before working at Vernier for the past 11 years, I was a high school teacher for about 20 years. So have a lot of classroom experience, taught grades 9 through 12 and a little bit of college. So, you know, I should be able to speak to your questions and do make sure you ask them. And then also with us today is Verl. Verl?
Hi, I'm Verl Walters. I'm celebrating my 20th year at Vernier this year. And before that, I worked at Texas Instruments for a few years. And before that, I taught for about 13 years, physics, math, and all things fun like that. So I'll be here to help out Fran. She's doing the main presenting. I'm here watching the chat and answering questions and helping out.
Thanks, Viral. All right, so what we're going to be doing today is first we're going to talk a little bit about our book, PEP. That is Physics Explorations and Projects. It is a guided inquiry-based book. Then we're going to talk about dynamics, cart, and track systems. Then we're going to do some labs, and it's going to be fun. So here's our book. It is specifically designed to be guided inquiry, which means that we actually have very limited student pages. Like the student pages that you can copy and give to your students are basically one-pagers for the most part. And a lot, you do need to read the instructor information to get an idea of what you should be presenting to your students and what you should be guiding them towards. And we also made this book to be technology agnostic. So that means that you can use a variety of methods, you can use a variety of materials, you can use materials from us or from other companies. We wanted to make this a book that everyone could use. So in general, we present students with a physical phenomenon. We provide teacher prompts for engaging the students, and we have suggestions for that. And then students are meant to design the investigation. And then we have our dynamics, carts, and tracks, and we've got a whole bunch of different ones, and I've got them here, so I'll also be showing them to you when we get to that part. So there's three options. We have the top one there with the bright tennis ball green or tennis ball yellow color is one of our GoDirect sensor carts. The cart itself collects the motion and force data, and I'll show you that. It's got an accelerometer in it as well, and that will work via Bluetooth with LabQuest and with graphical analysis. Then we've got the motion encoder system, and in that situation, there is an encoder in it, and then it sends the information via infrared directly to a receiver on the end of the track, and you can see that in the middle image. And then that receiver does need to be connected to an interface such as the LabQuest Mini or the LabQuest 3, and so that you can use that with either, again, LabQuest or graphical analysis. And then finally, it's kind of our least expensive version, but it's also, you can think of it as our most expensive version, the tracks and standard carts. You would have to collect data using a motion detector and a force sensor. And once you've purchased the track and the carts, and then additionally having to purchase the motion detectors and the force sensors, and then if you're going to do collisions, you might need multiples of those for each setup. It winds up being more expensive. And so Viral's putting some links in the chat, and then there's also a blog post that we have on choosing the right cart and track system for your physics classroom. There's a link to that in the folder. It's a document called resources, and that may help. And also, we're happy to help you. So if you already have some stuff and you want to figure out what additional stuff to get, we are very happy to have a conversation with you. We can do it over the phone, over Zoom. If you want to take it nice and slow, we can do it over email if you want. And we're also available by chat on our website. But we're all about helping you. So that's our different systems. And you can see, well, I'll show you some of this stuff. Let's see. So we're going to be, this is an image from the book. So we're going to have some sort of cart. We're going to have some sort of string and spring. And we're going to have some sort of way of measuring force and some sort of way of measuring position. So depending on what you have, then you get to use whatever it is that you have. And I'll go ahead and talking about this, when we're doing a guided inquiry and we want to present the phenomena, we're going to do a couple of things. This is actually probably one of our more complex guided inquiry experiments where you have to do a little bit more guidance than usual. So we're doing a couple things. We're doing a tour of the system, so the students should have some understanding of what a system is. There's recalling Hooke's law. You probably don't want to introduce Hooke's law with this. We're going to create multiple Hooke's law graphs. We're going to demonstrate what's happening, where the teacher is going to set up a situation and have the cart be made to move by the spring, and we'll record what the maximum velocity is. And then the challenge to the students is to have a different spring, and they have to achieve the same speed, and they have to figure out how to do that. So that's basically what gets set up. So I'm going to share a different screen now. So the screen I'm going to share has my setup over here. Did it go to the right screen?
Yes, that looks good to me.
Awesome, thank you. So over here, I have my cart. This is my sensor cart, and I'm using a sensor cart because it's going to be the easiest way for me to collect data in this demonstration. And it has the force sensor is inside here, and so I've got a hook that's screwed into that. This one does not have the hook screwed in. You can also screw in a bumper. You can screw in a hoop spring that we have, but there's you can just put whatever you need or not anything at all. Down here, this is the encoder wheel, and I'll try to bring that up a little bit. Maybe if I do it this way, you'll actually be able to see it. So this is the encoder wheel here, and it's on a spring. So it is going to rest against whatever surface is underneath the cart, whether that's the floor, whether that's a track, whether it's whatever you've got. And it's separate from the 4 regular wheels of the cart. We know, for example, that if you have something on 4 legs, if one leg there's something wrong with it, then you can still be stable on 3, but it's possible to be stable and have one wheel not touching. So by having a separate wheel with the spring, we make sure that we don't get any skips in the data. And then this is fun. These all come with these things. This is what we call an anti-roll peg, and this lets us put the cart down, and it's not going to roll off the table on us. So we actually sell these in 10 packs for pretty cheap, but if you have carts from us, then you can just give us a call or shoot us an email and ask us, hey, can I get some of those anti-roll pegs? And we'll just send them to you. So we're going to use the carts, but I just wanted to show you, you might also have carts like this. You might also have carts like this. And this is the same shape as this one, but it's got the encoder on it. And this encoder is actually optical with infrared LEDs and detectors that are on the stripes on the track, as opposed to having the little wheel. And the way that works, you'd have to have this receiver plugged in. They have to point at each other, and then you have to, there's a switch, and then you have it would send the data there. But we're not actually going to do that. We're going to do the sensor cart. So this is what I have set up with my hook. And the other things I have are some string, and I've started using this stuff. It's really bright. That's what I like about it. What I don't like about it is it feels a little bit sticky, because what this is waxed 0.5 millimeter polyester thread. 0.5 millimeters, a little thicker than your average thread. Another thing I like to use is upholstery thread that you can get. You might be able to get some on sale at Joann's if your local Joann's is still open. But upholstery thread is a nice, very not stretchy and fairly strong thread. I know people who swear by using fishing line or dental floss. I don't care for fishing line because I have a hard time tying knots in it. So I like thread. Do your own thing. So I've got a couple pieces of thread here. This other one, I've got a one here with 2 loops at the end. I've got another one here with 2 loops at the end, and one's long and one's short. And then I also have, put this on a piece of black paper, you can see that I actually have a spring here. I'm going to put the spring connected to both of these. There we are. And put that end over my ring stand here, which this is just a regular ring stand. I just stuck it at the end of the track. And there's multiple ways to do that as well. So, and then so the other string, I'm going to put at the other end. The other thing about the orange is I was trying to make it so it was kind of visible. Unfortunately, because the camera has to be kind of far away from this part, so it's not super visible. All right, so I've got it all attached. You can see the spring, and then when I remove this black piece of paper, now you can't see it at all, which is why I had the black piece of paper there. I guess you can kind of see it. All right, so I need to connect my sensor. So I'm going to hit the on button here, and I get this little red flashing LED, and that means that it's available to connect via Bluetooth. So I'm going to go up here to graphical analysis, start a new experiment, choose sensor data collection, and here it is in my list. If I were in a classroom, I would have a whole bunch of them showing up in the list, and students can read this ID way better than those of us who are already needing reading glasses, but there's an ID number on each one. And one thing you can do if you're in the downloaded version here is you can actually type in some of these digits. Like I've got a 4N in here. If I type in 4N into the filter device thing, that gives me just the thing that has a 4N in it. And so that's a way for students to make it easier to figure out which one is theirs to connect to. We had a question that someone who registered sent in that was, well, if you've got all of these devices and all of this Bluetooth going on, is there ever any trouble with that? We have not heard of anyone having trouble with it. People have been using these for a few years now, and it all seems to go great. You want with your cart, you do want to connect it via Bluetooth. For all of our sensors that are Go Direct, you can also connect via USB. But then if you connected the cart via USB, that would not be conducive to it rolling freely. So we don't suggest that. If you're using it just as a force sensor, then sure. But if you want to do position, then no. All right, so I've got it connected. It takes a moment to say hello and shake hands and everything. And then once it is, ignore the firmware thing. This is going to start blinking green instead of blinking red. So that's how I know that this is connected. If I want to make sure that this one's mine that's connected, I can hit on this little eye here and choose identify. And now it's actually flashing red and green. So I can tell, oh yeah, this is the one I'm connected to. But I'm done with that, and I'm done with this. Oops, I wasn't done. Sorry, my mistake. So I didn't want to dismiss that, and I did. So in order to get that back, I'm going to go down here to the bottom right corner and click on Sensor Setup. And because I care about my sensor channels here, and in addition to position, I also want to know how much force, because the first thing we're going to do is a Hooke's law experiment. So I need both position and force. Now I'm done. I get 3 graphs. I don't really want 3 graphs. I want something like 1 graph. So up here is I call it a box divided in 3 parts. Some people call it a window and a door. People call these things by different names, but this is the view menu. And so you can choose whether to show 1, 2, or 3 graphs. I want to show 1 graph. It generally picks whichever one was on the top, which was my force graph. But I also don't really want to graph force versus time. So I'm going to click on this, and I'm going to change that to force versus position. Now, all of our carts have an arrow on them with a plus X next to it. And that tells you which direction is the positive X direction. So that means if I'm pulling on this, I would get a positive force. But I'm going to pull this and I'm going to move the cart in the negative X direction, right? So when we talk about Hooke's law, we talk about the force of the spring being negative kx, right? This will give you that. But when we do the Hooke's law experiment and we talk about the spring constant, we normally have a graph with a positive slope, right? So in order to have a positive slope, I need the position positive direction to be that way and the force positive direction to be that way. So I'm going to go down here to my position meter, and this is where I can reverse it. And also when I start, I'm also going to zero it. And I'm going to zero the force. So zero the force, and then I'm going to get this. You know, maybe I'll just stick the paper under here just so that doesn't go in the little slot. All right, so then I get this so that it is almost about to stretch the spring, but not quite. And then I'm going to zero the cart as well. And then I'm going to go ahead and collect my data, and I'm just going to roll this back gently. Oh, look at that tiny graph. All right, so in order to see my tiny graph, I'm going to go down here to my zoom to all data, this magnifying glass down in the bottom left, and look at that beautiful Hooke's law graph. And doing this, I can very quickly find the slope of this by going and clicking on the little graph down here at the bottom left, choose apply curve fit, and then I'm going to choose linear because this looks a lot like a straight line, apply that, and now I get a slope of 5.93 newtons per meter. That is great. We advertise these particular springs. They come in a little box, and they've got 3 that are 15 and 3 that are 5. I call 5.93 close to 5. I mean, it's hard to get all of the springs exactly the same, but I call that close to 5. All right. So this would be something you might try this with different springs. If I go ahead and switch this spring out and put in the other type of spring, I gotta just do. Rural, how are we doing on questions? Are there any questions?
So far, you're doing a great job. No questions have come up.
All right. So here is another spring. It's the one that's nominally 15 newtons per meter, and I'm going to go ahead and zero my cart position. My force is already zeroed, and I'm going to collect for that one as well. All right. And then as you see this, I had a little bit of a jump here. That was the slack in the string getting taken up. So I'm not going to worry about that. And I'm going to just select the rest of this. And I can do a curve fit on just the linear part of it. So if I apply the curve fit to this part, then I'm getting 17.41, which again, I think that's pretty good. I hope you're seeing this all right. One thing when you're presenting and you've got graphical analysis maybe up on your screen somehow to display it for everyone, you can go into app preferences here and you can change the scale factor so that maybe it's easier for students to see. Just makes everything a little bit bigger in terms of the words and stuff. But anyway, here we've got 17.41, which I call that close to 15. All right, so lovely graphs. If I want to display both at once, I can go over here to this vertical axis label and click on it. This gives me what we call our plot manager, and we can do both of these at the same time. Because this is what we call the green cart, and I apologize for that. I always apologize for this. When we first did these carts, we wanted to pick colors that were distinct from each other, that colorblind people would be able to tell apart. And we didn't want it to be red and blue because we felt that those were already taken. So we made these two colors, which are technically chartreuse and teal, and we named this one yellow. So if you order this cart, it's got a Y at the end of the order code. And we named this one green. So if you order this cart, it's got a G in the order code. And we've been told that no, this one is green, the chartreuse one, and this one is blue. So I apologize. So anyway, these are you get both these colors because that's the blue, green, or teal cart. And I'm going to go ahead and change these colors so that they're colors that are easier to tell the difference on. And now I've got both of them with a linear fit on them, and I've got them in two different colors that are maybe, because I've still got that one. Hold on, let me just go over this again. This should fix itself. So yes, I like it. So now we had a teal highlight still on this one before, and now we've got the red highlight on it, so that's better. Okay, so we've done Hooke's law, gone over that with students, reminded them of how that works, and then it's time to actually look at how fast that we can make this go. So what I'm going to do is I'm going to choose how far to pull this back. And that's right at the 14 centimeter mark. So I'm going to choose to pull it back 3 centimeters. Oh, wait, sorry, the 16 centimeter mark. 14's over here. 16, so 15, 14, 13. I brought it back 3 centimeters. And I'm going to change this to, well, actually, I'm going to go ahead and do this, and then we'll look at the velocity graph. So I'm going to go ahead and collect and let it go. Yeah, force versus position is not very helpful in this case. But I'm going to change this. So this is versus time. And instead of force, we're going to look at velocity. All right. So my maximum magnitude of velocity is going to be right here. What I didn't do was reverse back the position sensor on the cart. So it's still going in the positive direction. It's still calling this the positive direction because I didn't change that. If you want to change it, you can, but it doesn't really matter. What's important is to get what this value is. So this peak value, I'm going to choose view statistics, and the minimum in this case is negative 0.261. So this is something that you'd want to write down so that all of the students can see it. Maybe put this on your whiteboard or something. V equals 0.261 meters per second. And now they have to figure out how they're going to use their different spring to get that same amount. And so what do you think, put this in the chat, what do you think that that the students are going to suggest? What are they going to suggest for what to do to get the same speed with a different spring? Okay, so pull it back at a different speed. Okay. Do energy conservation. Okay. If they already know how to do the elastic potential energy, then yes. They also might, if they're, pull it back a different distance, they'll try pulling it to the same location. Another thing they might try doing is just pulling it to the same force. Oh, this is terrible. I'm going to make the force a different color here. They might try pulling it to the same maximum force, right? So if I choose statistics for just that little bit, these statistics for that little bit, these statistics are for this bit. The maximum force here was 0.676 newtons. They might ask you what's that and try to pull theirs to the same amount of force. But yes, of course we know that what we really want them to do is, since this was the 15 newtons per meter that position, that they want to know if you pulled it back 3 centimeters, so pulling it back to that much, what's that area? And if someone had asked, can you make this into a calculus-based lesson? Yes, you can. You can have them, view the integral and actually get a value for that. So they're looking for a similar value for their integral. Now, because of the way I collected my data and got the taking up the slack in the string, that might not be quite right. They might need to extrapolate that line, which they can do. So if they've got a curve fit on here, and then they want to interpolate, interpolate is usually in between values, but if you've got a curve fit on it, you can also extrapolate. You can actually bring this all the way down to see what that would be here as well. So that tells you what your value you would be. You can even extrapolate beyond the data you collected as well. So if I wanted to know, all right, well, what would I have for force out here at 20 centimeters, for example, close to 20 centimeters. So lots of different options here. And so that's why I'm talking about, they might not immediately clock to having to do the same potential, the same elastic potential energy. So that could be a challenging part, which is why I say that this is one of our more difficult guided inquiry. You might have to guide them a little on this. When I do guided inquiry, because I don't teach it anymore, I would let students hear each other. Like, they're not trying to keep anything secret from each other. If one group comes up with something that's right and some other group overhears them, that's fine. That's great. That's how knowledge spreads. So I like that kind of thing. I like to encourage all students to work together. I just wanted to show you a couple things on here before I end this segment, because if you're doing this with one of these other carts, you would want to use our Go Direct Force and Acceleration, and either the encoder receiver or a motion detector. I have the Go Direct motion detector here, but it could be any of our motion detectors. And I would just put the motion detector at the end. We have, when you buy the cart and track system with these plastic carts, they come with one of these, which is a motion detector flag somewhere. Oh, here they are. And you can replace the little tabs with ones that have magnets in them. And then this will just stick on there like that. So that's something for, yeah, you can use it without that, but it's just more reliable that way. That only works if you've got the magnet tabs in there. And if you're using this one, first of all, we've got a completely different system here. You want to like get this all snugged up like that. But then we have to go low tech, and I have some tape and an index card, and I just put it on there. And you can do it that, well, I need some more tape to do the tape the other way too. I do this. And you can do it horizontally as well. It's just giving a flat surface because motion detectors work by ultrasound. And so waiting, it makes a tiny little pulse of ultrasound. It goes out and then it echoes off of something and it's waiting to hear that echo come back. It detects that and says, all right, well, it traveled 2 times the distance away from that. So we're going to divide that time in 2 and then use the speed of sound to figure out how far away it is. So they need something to bounce that echo off of. And then in this case, you would put your string up on this force sensor up here. And then do the same thing. You might need a shorter string. This actually won't detect something that's this close to it. It likes at least 15 to 20 centimeters. So might have to make this string shorter, but that's easy to do. We all have scissors. Probably.
Also, the cart track system comes with a bracket for mounting the motion detector off the track. So
it does. You can mount it way back here. Can you? No, you can't even see that. But there's basically a metal piece that you can put into the groove here and then mount it back off of the, thanks, Verl, off of the track. So lots of stuff there. All right. I'm gonna go back to my presentation. All right, so after that, we want to get up to doing collisions here. But in between that, we've got 3 more labs. So we're going from, what is it, lab 11 to lab 15. So kinetic energy and mass. Students should have experience with energy representation tools. We're not ever suggesting that these experiments are done outside of the context of your everyday teaching. So you're teaching about energy, you're teaching about systems. They should, before you do kinetic energy and mass, they should definitely have practice defining a system. Energy bar charts, LOL diagrams, maybe you do energy pie charts, maybe you do something else. But the goal is to determine, for that lab, is to determine a relationship between the mass and the velocity or speed. It's speed because you're squaring the velocity, so it's going to be positive anyway. Then we do a working kinetic energy one. So the students should already know the equation, but then going to specifically relate the work done by the spring to the kinetic energy. So here we're doing this, we're finding this relationship. It's not necessarily going to be the same thing. In this, the way we do it in experiment 13, instead of using the spring, use something else that's like a spring. So we use like our hoop springs, something like that. But we try to make sure students have experience with different stuff. And then finally, we do one on work done by gravity. And they should already have been introduced to gravitational potential energy. the goal is to conclude that work done by gravity and gravitational potential energy. So like, again, we're relating work done and energy storage kind of in both of the work and kinetic energy and work done by gravity. All right, so energy and collisions. And here's a picture where you can see that little flag there. You need two carts. You need some way to measure the velocity of each cart simultaneously, and you need ways to create elastic and inelastic collisions. So I'm going to use magnets. You could also use hoop springs. You could, there's probably another way to have an elastic bounce that I'm not thinking of. And then for the inelastic, I've got some Velcro. And so once again, with your students, you'd give them a tour of the system. So in this case, I'd have a couple of different carts, then doing a demonstration of a collision, maybe show them a couple of collisions. Maybe you've already done this with momentum. I don't know. But if you're in an energy unit, encourage the students to think about, all right, well, maybe we already looked at momentum. Can we look at energy? Is it going to behave the same way? Ask them some questions. They should make some predictions, and then challenge them to investigate different collisions through the lens of energy. And just so that you know, when we decided what we wanted to do with this, we decided that elastic collisions are collisions in which kinetic energy is conserved. Inelastic collisions are collisions in which kinetic energy is not conserved. And if you want to talk about specifically a collision where the objects involved are stuck together afterwards, we call that completely inelastic. And I know some people might say partially inelastic, or we wanted to make sure that we defined these the way we wanted to use them. Other textbooks might define them slightly differently. All right, back to the other thing. I'm trying to get through this because I know we said this would be over after 45 minutes, and I'm running out of time. So, all right, I'm going to start a new experiment here. And I'm going to get my yellow cart started. I'm going to get rid of this and this. All right, so my yellow cart is now blinking. I have to go here. It's going to automatically still connect to the green teal cart. So I'm going to say, all right, I also want to connect to this one. And I'm actually not going to use the force sensor. I'm just going to use the position sensor on here. So I'm going to get rid of force. And I'm going to say done. And then these are, oh, good, they're not reversed. So in order to have a coherent system, you're going to want to have the x direction the same direction for both of them. And it's important in all cases, but it's important here that you level the track so that if you set a cart at one place on the track, it's not going to go anywhere. These little things on the bottom, the legs, they help with that. And one thing that not a lot of people know, there's a little washer here that kind of screws in here also. It's more wiggly if you don't tighten the washer. So we recommend tightening the washer, and it's much less wiggly. And that's easier to do your collision. So these carts, oh, this cart doesn't have tabs in here. I'm going to go ahead and put some Velcro tabs. Oh, those have magnets. Those have magnets. Let me find some Velcro tabs that don't have magnets. They're probably, nope. Nope. All right. Oh, the Velcro tabs are at the other end. Okay. So put the Velcro tabs at this end because I'm going to be running into this. When I weighed this, it had tabs already in it. So I'm going to put those tabs back. All right. So I'm going to go ahead and I'm going to zero them both together, actually. 0, 0. You don't have to do this because you're just going to be looking at velocities, but I just like it because I like the way it looks. That's all. Isn't that beautiful? I just love looking at these graphs. So now we can look at velocity. I'm going to change these both to velocity up here and then just show one graph because all I care about, hello, let's try making it 3 graphs and then let's try making it 1 graph. There we go, 1 graph. So now we can look at these and look at what the velocity was right before the collision. You can actually use this examine bar to do that. It was going at 0.492, and then right after the collision, they were both going 0.237. We know the masses of each cart, and students can calculate the kinetic energy using the formula. It's best to do that in the data table. And what I would do is I would create a calculated column. And when you're doing a calculated column, then what you can do in Graphical Analysis Pro is you can do a custom expression. So if I'm going to do 1/2 times the mass times v squared, I can do 0.5 times, let's see, the yellow cart was 0.2779 kilograms. And then times velocity, this is a velocity y, and then I'm going to square that. Okay, oh, because I have to, got to be careful. You can only have one set of, I typed a quotation mark and that made there 2. But anyway, you can see that the columns showed up there. If I do apply, now I'll have a kinetic energy column here. I should actually probably rename that column options. I'm going to call this KEY so that I know that it's for the Y cart. I could do another one for the green cart where I do the velocity of the green cart. And then I can also make a column where I'm just adding 2 columns together so I get the total energy. And then what we care about looking at then is the total energy before the collision and then the total energy after the collision. I like being able to do these calculated columns. I think that's really useful. We are out of time already, so I'm going to stop sharing and go back to my little presentation here. I know Dylan has a survey for you, so please answer the survey. Please go to the resource folder for resources, lab instructions, and these slides. Verl, are there any last things that people asked that I should quick answer?
No, I think you got them all.
All right, awesome. Whew. 45 minutes was not quite enough, but that's okay.
All right, and I have a giveaway. So everyone who attended live today was entered into a giveaway. I used a random name selector, and today's winner of a sensor cart is Russ M. So congratulations, Russ.
Congratulations, Russ.
I am going to email you, so keep an eye out for an email from someone with an @Vernier email address. If you don't see it, check your spam. It might take me 30 minutes, so give me a little second and then I'll get that email shut off. I just need to get your shipping information and everything. So congratulations, Russ.
Thanks, everybody.
Thank you
Have a
all.
good evening.
And don't forget to give us feedback. We'd love to hear from you.
Yep, fill out the survey.
All right, everyone. Bye now. Thank you.